A few years ago, if you wanted a better AI model, the answer seemed obvious. Make it bigger. More parameters, more GPUs, more training data, more compute. And for a while, that strategy worked incredibly well. We went from models with a few billion parameters to tens of billions, then hundreds of billions, and eventually even larger systems. Every new generation seemed to prove the same thing. Bigger models were smarter models. But recently, something interesting has been happening. Some much smaller models are starting to perform at levels that would have required dramatically larger models only a short time ago. A model that fits on a single GPU can now write surprisingly good code, solve complex problems, understand long documents, use tools, and follow instructions much better than older models several times its size. So what changed? Did parameter count suddenly stop mattering? Not exactly. Bigger models still have major advantages. But the AI industry is learning how to get much more intelligence out of every parameter. And I think this is one of the most important changes happening in AI right now, especially if you care about local AI. Because if models keep getting more capable without getting dramatically larger, the future of AI may not require a data center for every useful task. It may fit on your laptop. To understand what's happening, we first need to talk about what a parameter actually represents. When we say a model has 7 billion, 32 billion, or 70 billion parameters, those parameters are basically numerical values learned during training. You can think of them as billions of tiny adjustable connections inside the neural network. During training, the model changes those values over and over until it becomes better at predicting what should come next. Historically, adding more parameters gave the model more capacity, more room to learn patterns, more room to store relationships, more room to represent complicated language, code, facts, and reasoning behavior. So naturally, bigger models often performed better, but there was always a hidden assumption. We assumed those parameters were being used efficiently, and that turns out not to be true. Two models can have exactly the same number of parameters and still have completely different levels of intelligence. One might be excellent, the other might be terrible. Why? Because parameter count tells me how much capacity a model has. It does not tell me how well that capacity was trained. Imagine two students. Both have the same size brain. One spends 4 years learning from carefully selected textbooks, practicing difficult problems, getting feedback, and correcting mistakes. The other spends 4 years reading random internet pages with no structure and no feedback. Their physical capacity might be similar. Their knowledge and skills will not be. Large language models are surprisingly similar in that sense. One of the biggest improvements in small models comes from better training data. In the early days of scaling, the goal was often to collect enormous amounts of text. More data was generally considered better. But internet data is messy. It contains duplicated pages, spam, low-quality writing, incorrect information, broken code, SEO content, machine-generated garbage, and millions of examples that may not teach the model very much. If I train a model on huge amounts of low-quality data, I'm spending compute without necessarily getting useful intelligence. So researchers have become much better at filtering training datasets. Instead of only asking, how many trillions of tokens do we have? An extra. They're asking, which tokens actually teach the model something useful? Or, that difference is enormous. A smaller model trained on carefully selected, high-quality data can sometimes beat a larger model trained less efficiently. And this is especially important for areas like coding and mathematics. If I want a model to become good at programming, throwing random web pages at it isn't enough. I want high-quality code. I want correct solutions. I want explanations. I want examples of debugging. I want different programming languages. I want difficult problems. And ideally, I want some way to verify that the answers are actually correct. The same idea applies to reasoning. One of the biggest changes in modern models is that training doesn't necessarily stop after the model learns to predict text. That initial phase, often called pre-training, gives the model a huge amount of general knowledge. But after that, there's another entire world of training. Post-training. And this is where small models can become dramatically more useful. During post-training, developers can teach the model how to follow instructions, how to answer questions clearly, how to use tools, how to solve problems step by step, how to avoid certain mistakes, and how to behave more like an assistant. Instead of just a text predictor, this means two models with the same parameter count can feel completely different. One might constantly misunderstand instructions. The other might feel surprisingly intelligent. The difference may not be the number of parameters at all. It may be what happened after pre-training. And reinforcement learning is becoming a big part of that. Instead of simply showing the model correct answers, researchers can let the model attempt tasks and then give it rewards based on whether it succeeds. This works especially well when the result can be verified. Take mathematics. The model solves a problem. We check whether the final answer is correct. If it is, reward. If not, try again. Coding works the same way. The model writes a program. Run the tests. If the tests pass, reward that behavior. Now imagine doing this millions of times. The model starts learning strategies for solving problems instead of simply imitating the style of answers found in training data. And this is one reason smaller models can suddenly look much smarter than their parameter count suggests. They're not just being trained to know more, they're being trained to use what they know more effectively. Another major technique is distillation. I think of distillation as a very smart student learning from a much more experienced teacher. Imagine I have an enormous frontier model that is extremely expensive to run. Maybe I don't want to deploy that model everywhere, but I can use it to generate high-quality examples. It can solve problems, explain reasoning, write code, create synthetic datasets, critique answers, compare different solutions. Then I use all of that output to train a much smaller model. The smaller model doesn't become identical to the teacher, but it can absorb a surprising amount of the teacher's behavior. This can massively improve small models. And the beautiful part is that the teacher model might only be needed during training. Once the smaller student model has learned from it, I can deploy the student on much cheaper hardware. Maybe one GPU, maybe a laptop, maybe eventually a phone. This changes the economics of AI. Instead of asking everyone to run the biggest model possible, we can use giant models to create better, smaller models. And there's another improvement that often gets overlooked. Model architecture itself is getting better. Not every parameter needs to be active for every token. This is where mixture of experts models become interesting. Imagine a model contains many different expert networks. One might be especially useful for code. Another might help with language. Another might handle certain reasoning patterns. Instead of activating every parameter every time the model generates a token, the system routes the token through only a subset of experts. So you might have a model with a huge total parameter count, but only a fraction of those parameters are active at once. That means the model can have more overall capacity without requiring the same amount of computation for every token. It's basically saying, why wake up the entire company when only 3 departments are needed for this task? That idea can make models much more efficient. And efficiency is now becoming almost as important as raw scale. There's also better tokenization, better attention mechanisms, better context handling, better training schedules, better optimizers, better synthetic data generation, better ways to prevent duplicated or useless training samples, better methods for teaching models to call external tools. None of these improvements sounds as dramatic as saying, we doubled the parameter count. But when you combine all of them, the effect can be huge. This is why comparing modern models purely by parameter count is becoming less useful. A 70B model is not automatically better than a 30B model. A 30B model is not automatically better than a 14B model. You need to know what the model was trained for. You need to know the quality of the data. You need to know the post-training method. You need to know whether it was optimized for coding, reasoning, chat, tool use, or something else. And you need to know what task you actually care about. A smaller coding model trained heavily on high-quality programming problems might destroy a much larger general-purpose model on coding tasks. But ask it about history, creative writing, or obscure knowledge, and the larger model might still win. So, when people say smaller models are becoming smarter, I don't think that means size no longer matters. It means intelligence per parameter is improving. That's a much more interesting way to think about it. How much useful capability can we extract from every billion parameters? That metric matters enormously for local AI, because model size determines memory requirements. If I can get the same useful performance from a 14B model instead of a 70B model, that changes everything. The memory requirement drops. The model becomes faster. Power consumption drops. Hardware gets cheaper. Latency improves. And suddenly, I can run the model locally. This is why I think small models are going to become increasingly important. There are billions of devices in the world that will never have access to 80GB data center GPUs, phones, laptops, cars, robots, industrial computers, home servers, security cameras, wearable devices. If AI is going to become integrated into all of those systems, we can't solve everything by making models bigger forever. We need models that are more efficient. Imagine an AI assistant running completely on your laptop. It can read your files without uploading them. It can summarize documents. It can search your notes. It can write code. It can operate software. It works on an airplane. It still works when your internet connection disappears, and there's no API bill every time you ask a question. For that kind of system, a smaller, highly optimized model might actually be better than a gigantic cloud model. There's another reason. Speed. Let's say I have two models. One huge model gives slightly better answers, but generates 5 tokens per second. A smaller model gives answers that are maybe 5% worse, but generates 50 tokens per second. For a chatbot, maybe I'm willing to wait. But what about an AI agent? An agent might call the model dozens or hundreds of times while completing one task. It might read a file, think, call a tool, read the result, think again, modify something, run another tool, check the output. If every model call is slow, the entire agent becomes painfully slow. In that environment, a fast, smaller model can actually be more useful than a larger, smarter one. This is where I think the future gets really interesting. We may stop looking for one giant model that does everything. Instead, we might have different models for different jobs. A tiny model handles simple classification. A small model handles everyday conversation. A coding model handles programming. A vision model handles images. A larger cloud model gets called only when the problem is genuinely difficult. Maybe an AI agent decides which model to use automatically. That could be much more efficient than sending every request to the largest model available. And this is already changing how I think about local hardware. A few years ago, if someone told me they wanted to build a powerful local AI system, my instinct would have been to say, get as much VRAM as possible. That's still good advice. But now I also ask another question. What models are you actually going to run? Because a well-trained modern 14B or 32B model can sometimes be so capable that you may not need the enormous hardware you originally imagined. And quantization pushes this even further. Take a smaller model and compress its weights from 16-bit to 8-bit or 4-bit. Now it uses dramatically less memory. If the model was already efficient, suddenly you have something very capable running inside maybe 8 GB, 12 GB, 16 GB, or 24 GB of VRAM. That's where local AI starts becoming practical for ordinary people. Of course, there are still limits. Small models usually have less total capacity. They may know fewer obscure facts. They can be more fragile on extremely difficult reasoning problems. They may struggle more with very long or complicated instructions. They can still hallucinate. And sometimes a genuinely enormous model is simply better. There's no trick that completely removes the benefits of scale. But what's changing is how big that gap is. If a 30B model can deliver 90 or 95% of the experience I need from a much larger model at a fraction of the memory and compute cost, that's a huge win. For most real-world applications, the goal isn't to win every benchmark. The goal is to get the task done, and I think that's the biggest reason the small model revolution matters. The industry spent years asking, how big can we make these models? Good. Now we're finally asking another question. How small can we make them without losing the intelligence we actually care about? Why? Better data, better post-training, reinforcement learning, distillation, better architectures, better tool use, better quantization. All of these techniques are pushing in the same direction. More intelligence from fewer resources. And if that trend continues, some of the most important AI models of the future may not be the biggest models in the world. They may be the models that are just smart enough, small enough, and fast enough to run everywhere. Because once powerful AI no longer requires a giant data center, the number of places we can use it becomes almost unlimited. And that might turn out to be a much bigger breakthrough than simply adding another 100 billion parameters.